In this video, I will talk about the magnetic force or the Lorentz force, which acts on a moving charge as the charge moves with a speed v in a magnetic field of strength B. A point here to note is that the magnetic field is B here and the charge is Q, and the Lorentz force is given by this equation, and this gives only the magnitude of the Lorentz force or the magnetic force on a charge Q moving with the velocity or speed v in a region of magnetic field B. Theta is the angle between the direction of velocity and magnetic field. Now, if theta is 0 or 180 degrees, that means when velocity vector and field vector are either parallel or opposite to each other, then the Lorentz force is 0. After learning about the magnitude of Lorentz force, let's talk about how to find out the direction of Lorentz force. The direction of the Lorentz force is always perpendicular to the plane formed by velocity and b vector. And for a positive charge, we can find out the direction of Lorentz force by using Fleming's right-hand rule. Sometimes it's also referred to as the right-hand rule type 2. We called it type 2 because the earlier rule that we had presented, and we had called that as the right-hand rule 1 or the thumb rule or the right-hand grip rule. So this is a little different than that. This rule is called the Fleming's rule, and it uses 3 fingers stretched out at 90 degrees to each other using the right hand. A little bit more about the right hand rule. As I was mentioning, the right hand rule connects the directions of Lorentz force, the magnetic field, and a charge that is moving in the magnetic field, and the charge has to be a positive charge. That's when the Fleming's right hand rule works. And if the charge is negative, then we'll have to modify the rule a little bit. This is the modification. For a negative charge, the Lorentz force is in the opposite direction to the direction indicated by the right hand rule, type 2, or the Fleming's right hand rule. So roughly in this rule, the right hand palm is stretched out in such a way that these 3 fingers are perpendicular to each other. The thumb, the index, and the middle finger are perpendicular to each other, and then they're stretched out in such a way that thumb points in the direction of velocity vector or the velocity of the positive charge, and the index finger points in the direction of the magnetic field present in the region, and the extended middle finger will point in the direction of the Lorentz force or a positive charge. If the charge is negative, according to this bullet, we'll have to reverse the direction of the middle finger. So this is the direction of the Lorentz force if the charge is negative. This slide again revisits the Fleming's rule that was briefly mentioned in the earlier slide. The first step you have to do is open the right palm in such a way that index finger and thumb point out at 90 degrees. Then rotate the right hand so that the thumb points in the direction of velocity, index finger points in the direction of magnetic field. When we do that, and the stretched out middle finger will point in the direction of Lorentz force for a positive charge, and for a negative charge the Lorentz force points in the opposite direction shown by the middle finger. That means for a positive charge the Lorentz force will point up like this. This is the Lorentz force. And for a negative charge, which I want to show by blue color or maybe black color, for negative charge the direction of the Lorentz force will be opposite to that of the middle finger. This is the direction of the Lorentz force on the negative charge. In this slide, let us do some examples of using the right hand thumb rule, or, oh sorry, not the thumb rule, but the right hand rule type 2, which is also referred to as the Fleming's rule. The Fleming's rule always uses 3 fingers which are stretched out in the right palm. So the question is, what is the direction of the magnetic force on a positive charge? So the charge is given to be positive, that moves as shown in each of the 6 cases. So in each of the 6 cases we are given the direction of velocity vector and the field vector, and we are asked to calculate the direction of the Lorentz force using the Fleming's rule. In picture A, if you were to stretch out the right palm with the 3 fingers shown here at the bottom, you will see that when you put your thumb downward along the negative y-axis, this is your thumb, and then if you stretch your index finger coming out of the screen shown by the dot, then the middle finger will point towards the left direction, indicating that for a positive charge the Lorentz force will kick the charge to the left. For picture B, if you were to extend the Fleming's right hand rule again, such that the velocity vector is pointed upward along the y-axis and the index finger is pointed to the right, showing the magnetic field, which is shown in the picture here, then you will see that the middle finger points into the screen, indicating that Lorentz force is pointing into the screen. For picture 3, we find that when we stretch out the Fleming's right hand rule with velocity pointing in the x-axis and using the thumb, and the field is pointing into the screen shown by the cross, then the index finger points along the positive y-axis, just like it's shown in the picture here. The picture works okay for part C. For part D, interestingly, we find that velocity vector is in the opposite direction to the left, and the field vector is to the right, and you will see that this is a tricky question because the angle is 180 degrees between them, so the force will be 0 according to our formula, because sine 180 is 0, and then because of that there is no Lorentz force on the charge in part D. In part E, similarly, you will find the Lorentz force is acting to the right, and for part F, the Lorentz force is acting downward. Make sure you check your answers. That's how we can use the Fleming's rule to figure out the direction, which connects the direction of velocity of the positive charge, the direction of the magnetic field, and the direction of the Lorentz force on the positive charge. This is the last slide of this video. in this, we do a problem of calculating the direction and magnitude of the Lorentz force. So the problem states that20suppose in a physics lab you rub a glass rod with silk and place a 20 nanocoulomb positive charge on the rod. And calculate the Lorentz force. So we need to calculate F on the rod due to the Earth's magnetic field. So we have to figure out what that value is. If you throw the rod with a horizontal velocity of, we know the velocity now, of 10 meters per second in the west direction. So if you were to look, west refers to left, so this is west. This is where the positively charged rod is being thrown, and this is north, that's where the Earth's magnetic field is present. And if you were to use the right hand rule, the Lorentz force will be pointing downward. So this is, so to say, into the screen for now, according to our picture. And this will be done. So that's the direction. And to get the magnitude, we simply use this formula to get the magnitude of the Lorentz force. Figured out the theta will be 90 degrees in this case, because the angle between the north direction and the west direction is 90 degrees. So this is like 90 degrees. So by putting in that formula, we can just figure out our answer is as a very small value.